Hi, everyone. Welcome to Module 4, Lesson 2, where we go in more depth on Lewis dot structures. So we're going to start off with the different types of bond, singles, double, triple bond, and what those look like with our Lewis dot structures. So a single bond has a sigma bond, which looks like that. We're going to talk more about those next time, but please make sure you write that down because what we're going to have to do with it later is important. And single bonds are not the shortest, actually the opposite. They are the longest bond length and they have the weakest bond strength. So if you remember back to how you do your Lewis dot structures, you draw your element and then starting, like you don't have to start at the top. I always start at the top. Go and give each one of its valence electrons on each side before you go back and pair them up. So carbon looks like that. Hydrogen has just one valence electron, so you'd have 4 of those. And then we want to pair them up. Hydrogen is an exception to the octet rule because it can only have 2. So CH4 would look like this. And so the carbon has 2, 4, 6, 8, and each one of those hydrogens has 2, and so it's happy. Then we come up with a double bond. It has 1 sigma and 1 pi bond. So 1 sigma and 1 pi, we all should know that symbol. Double bonds are shorter and stronger than single bonds. And so, for example, here we've got C2H4. Now you might be asking yourself, okay, how am I supposed to do this? But it's really symmetry, if you think about it. I've got 4 hydrogens and 2 carbons. I'm going to put 2 hydrogens on each carbon so that they're the same. And then you can notice there are 2 lonely electrons on each carbon. Those pair up. And now that you have 2 pairs of electrons in between the carbon, that's going to be a double bond. Now, keep in mind, the hydrogens can go anywhere around the carbon. It doesn't really matter because we'll talk about this later on. These Lewis dot structures help us determine the shape. And so while this may not look like anything shape-wise, we'll come back to that. Okay, so that's double. So let's look at triple. A triple bond has 1 sigma and 1 pi bond, and 2 pi bonds, excuse me. And they are the shortest and the strongest of those 3 types. So we have C2H2, so 2 carbons, and then 2 hydrogens. So that's going to be a hydrogen on each carbon. And then you'll notice there are 3 lonely electrons on each carbon. And so they'll pair up, and now you'll have 6. I can put an H here. I can put an H here. The important part is that I have 6 in between. So now if you look at this carbon right here, it has 8, 6, 7, 8. The hydrogen has 2. This carbon has 8. That hydrogen has 2. So remember, with covalent, they're sharing electrons. So they go to both of them. Dots are great, but we can also show pairs of electrons as lines. So if I was CH4, I would just be like this. C2H2 for a double bond would have 2 lines, and then a triple bond would have 3 lines. And so you can really do it either way. If there were lone pairs, you still have to draw the lone pairs out as dots. But I'm going to be using lines when I do this because it is faster. Okay. So let's go ahead and do this one. I'm going to leave the space up here so I can draw. So let's do an example of ClO4, -1. So it's an ion. Remember, if it's an ion, we need to put it in brackets with charge. Now, here are the steps that we typically do when we're doing this for more complicated ones, because this one's going to be more complicated than the easy ones that we've seen before. Step number 1, count up valence electrons. Okay, so ClO4, so that's 7 plus 6 times 4. And since it's a negative charge, I'm adding another electron, so I have 32 valence electrons to work with. Question number 2, or the second thing you have to ask yourself is, what goes in the middle? So what's the central atom? For this compound, ClO4, -1, it should be easy because there's only one chlorine and that thing's going to be in the middle. If you have something that has one, like a bunch of things with just one element or whatever, so if it's not that, it's going to be the most electronegative element. I'm going to write if it's not obvious. Okay, so in this case, we're going to have chlorine in the middle. So then what we do is we then bond everything to the central atom. And make it happy. And happy means as many electrons as it wants, which is typically 8. So if I'm going to take chlorine, I'm going to bond my 4 oxygens. Okay, so chlorine will now have 8, and I'm going to give my oxygens their lone pairs so that they can have 8. And now I know it's not easy for you to see my lone pairs, my dots, but make sure your dots look like they're meant to be there. Maybe I can make this, no, I can't do, well, let's see. That's too much, that's not good. We'll just, they're there, just trust me. So we said things that have a charge go in brackets, and I put the charge. And then the fourth thing you have to say is ask yourself, is everyone happy? Did I use all of my valence electrons? Okay, so I have 32, 8, 16, 24, 32. So everything has 8. I've used all 32 electrons. So that's in a yes and a yes. And then the fifth thing, is this the best possible structure? In order to figure that out, we have to look at something called formal charge. Now, formal charge are not in these notes, so I'm going to go to a new piece of paper so we can talk about formal charge. So the formal, what is formal charge? It's just basically helps us determine the most correct Lewis dot structure. And there's an equation that we can solve for. So formal charge is equal to, you take the number of valence electrons, you subtract that from non-bonding electrons, which are our lone pairs, plus our bonding electrons divided by 2. Now, if you go ahead and Google formal charge, there are many different formulas that all work out to be the same thing. This is just the one that I like to choose. So we do a formal charge for each, what is it? Unique is the word I want to use. For unique element in the compound. Okay, so we want as many, I'm just going to abbreviate formal charge of 0 as possible. What other things about this? If you have an ion, the formal charge must add up to be the charge of the ion. And typically, the more electronegative element would want the negative charge. Okay, so I have to clear this. This is probably a good point to pause. To get all this stuff down. So I'm just going to clear this. And then I'm going to write the formal charge equation again. Oops. Okay. So here's the structure that we had from before. And you'll notice I have two uniquely bonded atoms. I have the oxygen and the chlorine, because all of the chlorines are bonded the same. So I have to just do a formal charge for the oxygen and a formal charge for the chlorine. So for oxygen, oxygen has 6 valence electrons. From that, if we look at this, non-bonding electrons would be lone electrons. So 1, 2, 3, 4, 5, 6, plus bonding electrons, 2 divided by 2, which gives me -1. So this is a -1, -1, -1, -1. Okay. So far, not great, because we said we wanted as many zeros as possible. Okay. Well, I guess we should do chlorine. This is already telling us it's not going to be great. Chlorine has 7 valence electrons, minus it has no lone pairs, plus 2, 4, 6, 8 divided by 2, which is +3. So overall, it adds up to be the charge, but this is not the best. This is clearly not the best. Everything has a formal charge. We want zeros. Zeros are great. So what can I do to make this structure different? I don't have any more electrons yet anywhere. Everything's happy the way it's drawn. But what we can do is we can do double bonds. Okay, so chlorine can have more than 8 electrons around it. Why? We're going to talk about in our exceptions, but just keep this in mind. Chlorine can have more than 8 valence electrons. So I'm just going to do all double bonds. Let's see what doing all double bonds gives us. So again, I'm going to have to put it in brackets with our charge. And now every oxygen will only have 2 lone pairs. You see, each oxygen still has 8. Okay, the chlorine can have more than 8, and I still use all 32 electrons. So now let's try our oxygen and our chlorine formal charge now. So oxygen 6 minus. So now they have 4 lonely electrons plus 4 bonding electrons divided by 2. That gives me 0. That's a good sign. Okay, if chlorine's 0, or no, if chlorine's -1, then this is going to be the winner. 7 minus, still no valence electrons, or no lone pairs. 2, 4, 6, 8, 10, 12, 14. 16 divided by 2 is 8. 7 minus 8 is, oh my goodness, -1. And this is going to be your most correct structure based off of our formal charge. It's truly not that difficult, and it's a good check to make sure that what you've done is correct. Okay, and we'll do more throughout, but that's it for now for that. Let's go back to our notes here and talk about our exceptions. So exceptions to our rules. So again, Most things want 8. We know hydrogen, helium only want 2. So nitrogen, the element nitrogen, one of its exceptions that it can be is that it can have an odd number of valence electrons. So if I count this up, it's going to have 5 from nitrogen, 6 from oxygen, which gives me an 11. That's an odd number. The structure for this looks like this. And then nitrogen will have 1 lonely electron. Would I expect you to be able to draw that one? Not really, but just showing you that nitrogen, it is possible for it to have an odd number and less than 8 and still be happy. The central atom can have less than an octet. Okay, so BF3. Boron has 3, fluorine has 7 times 3, which gives me a total of what? 7, 14, 21, 22, 23, so 24 valence electrons. Now, boron, with its 3 valence electrons, it's special because all it really wants, I don't know why I just drew a C, what it really wants to do is just pair up those 3 and be done with it. So boron can bond with the fluorine. And then we got 8, 16, 24. The fluorines are all happy. Boron is okay with less than 8. Boom, there you go. Okay, and then the ones that we're going to see most often are an essential atom that has more than 8. So just like we saw with that chlorine, it had more than 8. Why? So this is important that we understand this concept. How can it have more than 8? Well, if the d orbital is present, there is room for what we call expanded octet. So if the d orbital is present, there is room for an expanded octet. So the d orbital is present in the 3rd energy level or higher. So if you have an element in the 3rd energy level, it is possible for it to break the octet with more than 8 because the d orbital, it's just extra space to basically shove those extra electrons. So let's look at some examples. So xenon tetrafluoride. Xenon has 8 plus 7 times 4, which gives me 36. Now you should already realize that I'm going to break the octet rule because xenon already has 8, so noble gases are going to be wonky. So we'll start with xenon. I know that goes in the middle because there's only 1. Bond my 4 fluorines. Make my fluorines happy. Again, make sure your lone pairs look like they're meant to be there and not just like you dropped your pencil. It's hard to do it on the computer screen. Okay, so technically everything's happy. Xenon has 8. All of the fluorine have 8. And how many did I use? 8, 16, 24, 32. So I used 32. I have 4 valence electrons left. What can I do with them? Well, fluorine cannot break the octet rule. So it's happy with its 8. So that means I can put lone pairs around xenon. I'm going to put 2 lone pairs around xenon. Doesn't really matter where. But now you can see that xenon breaks the octet rule with 2, 4, 6, 8, 10, 12 electrons. The next 2 examples you can see, we're bonding 5 and 6 things to the central atom. Clearly, it's going to break the octet rule. 5 plus 7 times 5 gives me 40 for PCl5. Again, phosphorus is in the center. I know the shape of this molecule, so that's why I drew the lines where I did. And again, make your dots look like dots. It's just really hard to with this pen. So 8, 16, 24, 32, 40. Everyone's happy. Phosphorus is in the 3rd or energy level or higher, so it can break the octet rule. Same thing with sulfur. So for sulfur hexafluoride, 1, 2, 3, 4, 5, 6. We always want to make sure we're putting our lone pairs. Okay, and there we go. We've done the same things. And then one other thing that's super important is CNOPs. CNOPs, carbon, nitrogen, oxygen, phosphorus, and sulfur. These like multiple bonds, like a double or a triple bond. Okay, so keep that in your mind while you're working with these things, that carbon, nitrogen, oxygen, phosphorus, and sulfur indeed like multiple bonds. Okay, so what we have to do, I'm going to clear this, and then I'm going to just scroll because something here is next. The next thing I want to talk about here is a resonance structure. I know this is in bad order, but resonance structure. So resonance structures refer to bonding in molecules or ions that cannot be correctly represented by one single Lewis structure. So resonance structures are stronger than single bonds, but weaker than double bonds. And in between your molecules, you actually do a double-sided arrow. And I'm going to show you what that looks like with the example of ozone. Ozone is O3, and it has a total of 18 valence electrons. So let's see, if I just tried to bond 3 oxygens. Okay, so let's see. So we'll try to make these happy. 2, 4, 6, 8, 10, 12, 14, 16, 17, 18. Okay, I've used all 18 of my electrons. The side oxygens are happy, but the one in the middle is not happy. Okay, it's not happy because it only has 2, 4, 6 electrons. It needs 2 more. Okay, well, what is the only option? Since we don't have any electrons left over, we can take some of these lone pairs and turn it into a double bond. But my question is, would it be these electrons turning into a lone pair, or would it be electrons from this oxygen turning into a lone pair? The answer is both. It doesn't matter, okay? Since I have that option, I have to show that both are correct. So to do that, we do our resonance structure. So we're going to do a double bond oxygen here. So 2, 4, 6, 8, 10, 12, 14, 16, 18. But then I'm going to draw a different structure over right next to it that shows that the double bond can actually be on the other oxygen. So when you have the opportunity to draw a double bond, and you have 2 options, you have to show both options. And so basically with resonance structure, you put it in brackets, and then you just do a double-sided arrow. And that shows that both structures are technically correct because you can have the double bond in between either oxygen. And that makes a resonance structure. You got to show both. Okay, and then just scrolling back up here, we've got one last thing to talk about, and that is the sigma and pi bonds. So when 2 atoms combine, it forms a molecular orbital from the atomic orbitals. So basically there's overlapping in s and p orbitals that give us a molecular orbital, an overall orbital. You can see, so sigma bonds, remember, are drawn like that. And it says when 2 atomic orbitals combine to form a molecular orbital that's symmetrical around the axis containing 2 nuclei, a sigma bond is formed. You can see in this little diagram, you've got some different options, an S and an S, an S and a P, or 2 P's, and it's that overlap that forms a sigma bond. A pi bond, bonding electrons are most likely to be found in, and this is straight from the textbook because I couldn't make this up if I wanted to, found in a sausage-shaped region above and below the bond axis of the bond atoms. These bonds are weaker than sigma bonds. So basically you got 2 p orbitals that overlap laterally. So it's going to have overlap like this, where your nuclei are right here in this plane. And so that's going to give you a pi bond. What do we need to do with this? we simply need to be able to count up the number of sigma and pi bonds in a molecule. That's all we want to be able to do with that. So remember, a single bond equals 1 sigma. A double bond equals 1 sigma and 1 pi. And a triple bond, 1 sigma and 2 pi. So if I had SI, I would have 3 sigma bonds, 1 for that single bond, 1 for that single bond, 1 for that triple bond, and then 2 pi bonds from the triple bond. And that's all you need to know about sigma and pi bonds. I'm going to keep it very simple. All right, and that's it for this lesson. I know it was a little longer, but there are a lot of structures in there. Remember, as always, if you have any questions, you come and ask me in class, in the chat. And there are also those other resources to help you if you are still stuck. But yeah, we'll see you back in class.